Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is Ramsey theory, the basics of ideas of what Ramsey theory is all about. So let's get started with a motivating example. This is a typical one that you will hear anytime you listen to something about Ramsey theory. So let's say that you're on a social media platform, and on this platform, users can either be friends or not. So two people can be connected or not. Let's say that you pick 6 arbitrary users on this platform. You just pick 6 random people, and I will have a prediction for you. What I'm going to predict is that no matter who you picked, you either will be able to find 3 of those 6 people such that each pair of them are friends with each other. So each pair of those 3 people are friends with each other. Or if you can't do that, you definitely will be then able to find 3 users so that none of them are friends with each other. I'm not saying that go out there and you can find 3 such people somewhere on the platform. What I'm saying that is, as soon as you give me any 6 people, from among those 6, I'll be able to tell you that there's at least, I'm going to be able to do one of these things. Either find 3 people such that each pair is friends with each other, or 3 people such that none of them are friends with each other. By the way, in mathematics, whenever we say or, it's an inclusive or, so it could be both. Maybe I can do both. Maybe I can find you 3 people such that all 3 are friends with each other, and 3 people such that none of them are friends with each other. But I will be able to do at least one or the other. Now, why would that be? This is what sort of starts the Ramsey theory discussion, is that how would I possibly know? You picked a random group of people. Maybe you went out of your way to find 6 people in a way that my prediction is not true, but I'm going to tell you that my prediction is true no matter what you say. So before we answer that question, meaning that before I prove to you that my prediction is always true and it's a certainty, is not a probabilistic thing, I want to reformulate the problem, and I want to reformulate it in terms of graphs. So we're going to construct a graph, make a graph. We're going to put 6 vertices for each person that you picked from that social media platform, and then we're going to put edges between them. If you're not familiar with the vocabulary of graph theory, watch my video on basic graph theory vocabulary. I'm going to put a blue edge between 2 vertices if the 2 vertices are friends. Remember, each vertex is representing one of the users, and I've got 6 of those. And so if 2 of them are friends, I'll put a blue edge between them. And I will put a red edge if they're not friends, if those 2 vertices are not friends. So if I do that, then I've got my 6 vertices, my 6 people, and I've made connections, edges between every pair of them. But some of those connections are blue, some of them are red. Blues represent friendship, edges represent they don't know each other. And so the graph that I have is what we call the complete graph of order 6. It has 6 vertices, and it has all the possible edges, no double edges or loops. That's called K6, the complete graph of order 6. But it has the property that it has colored edges, that its edges are colored one of 2 colors, blue or red. And what am I looking for? I'm looking for 3 vertices such that all of the edges between them is blue. That would mean that every pair of them know each other, or every edge between them is red, meaning that none of them know each other. Therefore, we have colored the edges with 2 colors, and I'm looking for a monochromatic triangle, a triangle that it's all blue or all red, that all of its edges are blue or all of its edges are red. When I say monochromatic triangle, I'm talking about the edges of the triangle all having the same color. So the claim that I made, the prediction I made, comes down to this. If you take a K6, a complete graph of order 6 with 6 vertices, and if you take each edge and decide on a color, whichever way you want, this one is going to be blue, that one is going to be red, and so forth, I'm guaranteeing you that there will be either a blue triangle or a red triangle, no matter how you do it. So let's see, what do I mean? So here's maybe my 6 people, A, B, C, D, E, F. And here's K6. Here's all the possible edges between them. Each one of these is going to be either friendship or not. And maybe A is friends with 3 people. And so I put blue edges. And then therefore, then the other 2 edges are going to be red because A doesn't know D and F. Okay, and I continue doing that. I continue deciding whether or not people are friends or not. And I'm doing this arbitrarily. You could be not arbitrary and try to stymie me and make sure that I fail, in the sense that there's no monochromatic triangles. And you might want to stop the video and try to give it a try to see if you can do that. So for example, maybe B and C do not know each other, C and D do, B and E do not. See, so far I do not have any monochromatic triangles. E and F maybe know each other, and so do E and D. All right. C and F do not know each other. I'm just randomly coloring these. You could do it your own way if you would like. And maybe B and D also don't know each other. And let's see, one more, and B and F maybe do know each other. And see, so far, if you look in this set of connections, there is no monochromatic triangle. There's no three people such that every two of them know each other, or three people such that none of them know each other. But now, when I want to do the next one, I'm stuck. So for example, if you look at the connection between C and E, if I make that blue, meaning if I say C and E know each other, then I have the blue triangle CDE. C, D, and E are three people, and they all know each other. And if I make it red, then CEB is a red triangle. And they all know each other. They all not know each other. Each pair of them do not know each other. So I'm stuck. And in fact, when I put the other edge in, I will get an additional monochromatic triangles. In fact, what I'm claiming is that this is going to happen no matter how you do the coloring. You should not, wasn't a proof. All this was that this sort of random way I did it did not work, meaning that I did get a monochromatic triangle. You might say, well, maybe you just rigged it from the beginning. You started in a way that you knew was going to cause you trouble. If you were more careful, you could have avoided those monochromatic triangles. And the claim is that that's not the case. In fact, it's also possible, with a different argument than the one I'm going to give you, with one that's in my book as a part of a mini project, you can prove that in a K6, if you color the edges with two colors, you will always have at least two monochromatic triangles, not just one, but two. In this case, for example, here we have a red one and a blue one. I can't tell you that I will have a red one and a blue one, or two blue ones or two red ones, or even a red one and a blue one, because you might, for example, color everything blue, then I won't have any red ones. Or you might color, if I say, well, then you're going to get a blue one, you might color everything red, then I won't have red. So that or is important. I'm saying that I'm giving myself some flexibility. Either I can find a blue triangle, or I can find a red triangle, or I can do both. Again, or is always inclusive. Okay, so again, before we actually prove the result, I'm going to introduce a notation. So the claim you're having is that if you color the edges of K6 with red and blue arbitrarily, then you're guaranteed a red K3 or a blue K3. That's the thing that we want to do. But instead of having to say that over and over again, I will want to have introduce a mathematical notation that says this claim. And the shorthand notation for this claim is going to be that K6 arrows to K3 or K3. So I'll write K6 arrows to K3 or K3. Now, this is a statement, may be true, may be false, but what it says is this statement here, K6 arrows K3 comma K3, that's the way I read it, K6 arrows to K3 or K3, means that it was, what is it? It's the same claim as before, that if you start with a K6, color the edges using two colors, and I know it's two colors because there's a K3 and a K3, there's two things, then I have a monochromatic, I have a blue K3 or a red K3. That's what this shorthand notation says. This is called the arrow notation. And again, I read it as K6 arrows to K3 or K3. Okay, now that we have all that in place, I'm going to now prove to you that K6 does indeed arrow to K3 or K3. This needs a proof. Just writing it down doesn't mean it's true. I have to now prove it to you. And again, because this is you haven't heard this notation before, let me repeat to you what that means. It means that if you color the edges of K6 with red and blue arbitrarily, then you're guaranteed a red K3 or a blue K3. This is what we're trying to prove. And so here's the proof. I'm not going to write it down, but I'm going to draw it for you. So here's my K6. all the edges between 6 vertices, no double edges or loops. That's what a complete graph is. And then I'm going to color the edges with red and blue arbitrarily. I can't actually do the coloring because I don't know how you might color this. So you walk through the door and do the coloring for me. I have to convince you that no matter what coloring you do, there will be a red K3 or a blue K3. This is what I'm going to say. I'm going to say focus on that vertex A, the first one, A. That vertex has how many edges coming out of it? There are 5 edges coming out of it. Okay. Now these edges you colored either red or blue. And I don't know how you might have done them all red, all blue, maybe some of them red, some of them blue, and so on. What I can say is that you use the same color on at least 3 of them. So you couldn't have just done 2 blue and 2 red because there's 5 things. This is sort of the pigeonhole principle. If you just do 2 blue and 2 red, then you're left with 1 more. So you have to have at least done 3 blue or 3 red. You might have done more than 3 blue, 4 blue, 5 blue, but at least 3 blue, or if not that, 3 red. There's symmetry between red and blue. It doesn't really matter which one. The argument is going to be similar either way. So let's assume that you did 3 blue ones. Again, you might have done more than 3 blue ones, but at least 3 of the same color. And without loss of generality, I'm saying that that color is blue. And so, for example, it might be that you've done the other 2 red, but maybe not. I don't actually care what the other 2 are. What I'm going to care about is the other ends of those blue edges. So I'm going to concentrate on B, C, and E in this graph. I mean, it doesn't have to be those 3 particular ones, but there will be 3 vertices other than A that are connected to A by a blue edge. And then what am I going to say? I'm going to say, well, there's a triangle among them, but I don't know what colors you used. I'm going to say, well, maybe use the blue color somewhere. So maybe use the, but if you did use that BC as a blue, then I've got my blue triangle already. Then ABC is a blue triangle. But maybe you didn't use that blue there. Maybe you use the blue here. Well, if you CE was a blue triangle, blue edge, then I would have that ACE is a blue triangle. And the same with the last one. If BE was blue, then ABE would have been blue. The point is that if you use blue on any of those edges, I will have a blue triangle. So you trying to stymie and make sure that I'm not getting a monochromatic triangle will say, okay, well, I won't use blue. But if you don't use blue, you're going to reuse red, and then I've got my red triangle, and then BCE is a red triangle. This is a lovely proof, although you may have heard it. It's now everyone knows about it, but it's a lovely proof that proves that if you color the edges of K6 with red and blue arbitrarily, you are guaranteed a red K3 or a blue K3. Again, you might want to try proving that there's actually 2 monochromatic triangles in no matter how you do it. That's a little bit of a different proof. It's not the same kind of a proof. The best proof I know is a counting proof, but counting multicolored triangles and then trying to figure out how many are left. Okay, continuing, I'm going to now actually want to prove to you that K5 doesn't arrow to K3 comma K3 or K3. So and some of that is so to make sure that we understand this arrow notation well, but some of it is because I want to make a point later that K6 was sort of important there. Okay, so what does it mean to say K5 doesn't arrow to K3 or K3? Well, it means that if you color the edges of a K5, now what's a K5? A complete graph on 5 vertices. So you have 5 vertices and all the edges between them. If you color those edges with red and blue arbitrarily, then you're not guaranteed a red K3 or a blue K3. You're not guaranteed that. It might not happen. So if I want to not say that in a negative way, then the way to say this is to say that it's possible to color the edges of K5 with red and blue in a way that there's no red K3, no blue K3. So the positive statement is that you can color K5 with 2 colors and avoid a monochromatic triangle. So to prove this actually is a little bit different than the previous proof. The previous proof was that no matter who does the coloring, we are guaranteeing a monochromatic triangle. Here we're saying it's possible to color the edges in such a way that there is no monochromatic polynomial. And the proof of the pudding is in the eating. All I have to do is show you how to do that. So here's a K5, 5 vertices and every edge between them. Now, of course, it's possible to draw in a way that I do get a blue triangle. I might make those three blue, and then I would get a blue triangle. That's not the point. The point is that there is at least one way to color it such that there is no monochromatic triangle. And I'm just going to show you. So I'm going to make blue all the edges on the outside, and I'm going to make red all the edges in the inside. And if you look at that, stare at that long enough, you'll see there are no monochromatic triangles. There's no blue triangle, and there is no red triangle. So K5 does not arrow to K3 or K3. So that statement, K5 doesn't arrow to K3 or K3, is a true statement. You can write as many of these statements as you like. Some of them will be true, some of them will be false. If they're true, they need a proof. If they're false, they need an example, like the one that I just showed you here. Okay, so we showed that K6 arrows to K3 or K3, and K5 doesn't arrow to K3 or K3. That says that 6 is some kind of a threshold. Of course, if you go above 6, like if you have not 6 people, but 8 people, then you will have a monochromatic triangle with a vengeance. Because if you have 8 people, just ignore 2 of them, you have 6 of them, and just among them you will find a monochromatic triangle. Leave alone the other extra 2. Presumably, you will be able even to prove that you can get more triangles. But if you have 5 or fewer, then you're not going to have a monochromatic. You're not guaranteed a monochromatic triangle. You might, but you're not guaranteed a monochromatic triangle. So 6 is going to be a threshold, and that number matters to us. And we denote that by saying R of 3, 3 is 6. Now, and R of 3, 3 is what's called a Ramsey number. So the 3, 3 says that those 2 3s says what we were wishing for. We were hoping that we would get a monochromatic K3 or a monochromatic K3. R 3, 3 tells us the threshold, the place that if our system is big enough, our Kn is big enough for us to achieve that. This whole theory started with Frank Ramsey, who didn't live that long, but wrote important papers in mathematics, in philosophy, and in economics. In mathematics, this whole Ramsey theory is a part of a paper he wrote on logic. In philosophy, he was actually good friends with Wittgenstein, and he was also a student of John Maynard Keynes. And in fact, in economics, Ramsey's growth model still talked about in neoclassical economics. It's something that people talk about in micro and macro classes. Okay, so Ramsey's theory's main idea, if just sort of this is an intuitive way of thinking about it, is that if your system is large enough and complex enough, you will be able to find almost any pattern. So for example, if you look up in the sky and you see all these stars, there's so many of them that you're guaranteed to, if you can decide that you want to see a lion, and you're going to be able to find it. You're going to want to find a camel, and you'll be able to find it. Whatever pattern you want among those, somewhere you'll be able to find, just because it's complex enough. In other words, in places where you might see chaos, there's actually order. So if your system is large enough, even if it looks chaotic, there's more order in it than first meets the eye. That's sort of the general idea, but we want to make that a little bit more precise. So first of all, let's generalize. Now, we proved that K6 arrows to K3, K3, but K5 doesn't. But what else can I ask? Well, we can use the arrow notation to ask other questions. So for example, you can ask, does K9 arrow to K4 or K4? You can ask that. So what does that mean? If I take a K9, 9 vertices, and draw all the edges between them, then color all the edges using blue and red, am I guaranteed a blue K4 or a red K4? A blue K4 means 4 vertices such that every pair of edges between them is blue, and a red K4 means 4 vertices such that every edge between them is red. Am I guaranteed that? And the answer to that is no. In fact, if you almost anything you write down, probably the answer to it is no. And how would I prove that? Well, you would have to come up with an example. I'm not going to do that right now. In a later video, we will talk about this particular question. But right now, I just want to make a point. However, it can be proved. I'm not proving it to you now. We'll prove it in a later video that K18 does arrow to K4, K4. So what does that mean? That means that if you take 18 vertices, draw all the edges between them, color them using 2 colors, then you are guaranteed a blue K4 or a red K4. Again, the system has to be big enough and complex enough for getting a, depending on your wish. If your wish was a triangle, monochromatic triangle, then having 6 was large enough. But if your wish is a monochromatic K4, then you've got to go to a system that's as big as 18, has 18 things in it. And of course, anything bigger would work. Anything smaller apparently doesn't work. I mean, it doesn't work because there's an example that shows that K17 does not arrow to K4 comma K4. Again, in a later video, we'll go into that. So the way we want to think about that is that R44 is 18. So again, those Ramsey numbers, I will define it more formally in a second. Those Ramsey numbers are the threshold numbers, the place where our wishes come true. So when we say R44, we are saying what our wishes are, a blue K4 or a red K4, and R44, the answer tells you when your wish comes true. Well, if you have a K18, then your wish comes true. If it's smaller, no, you might be lucky or not, but if it's bigger, or bigger, then you're good. We can also vary our wishes. We don't have to want the same thing for the blue and the red. We could ask for different things. For example, we could ask, what's R58? And what would we mean by that? By that, first of all, it's not clear it even exists. There is such a number. But if it did exist, it would be the smallest integer n such that kn arrows to k5 comma k8. What does that mean? If you take n vertices, draw all the edges between them, color them using blue and red, am I guaranteed a blue k5 or a red k8? If I am guaranteed, then that n is good. And R58 is the smallest good n, the n that will work. If I'm not guaranteed, then that means that I picked the too small of n. But, to be honest, it's not clear at all that such a number even exists. It doesn't clear that if you make your system big enough that you will get an answer yes. I mean, I said something like that for K4 comma or K4, you have to go to 18. But why would that be? Why? Maybe if I want K5 or K8, I've got to go to infinity. I just keep going and never get it. So the first place is to actually show that these numbers do exist. So first of all, let's make sure that we understand what the arrow notation is saying. So if I say Ks arrows to Kn or Km, I mean, this is a claim, and maybe true or false, but what is it? The claim is that if you arbitrarily color the edges of a Ks, a complete graph with S vertices of order S, then using two colors, blue and red, blue is the first color, red is the second color, then you're guaranteed a blue Kn or a red Km. I'm not saying that the Kn can be blue or red. If you're going to give me a Kn, it has to be blue. And the Km you're going to give me has to be red. So I'm saying a blue Kn or a red Km or both. I mean, if that both happens, again, or in mathematics is always inclusive. So Ramsey's theorem says that such a number, if you go S is large enough, this will happen. So it says that if you start with n and m positive integers, those are your wishes, your two wishes. You want a blue Kn or a red Km. And Ramsey tells you that there exists a positive integer S. It might be very large, and it definitely depends on n and m, such that such that Ks will arrow to Kn comma Km. So Ramsey's theorem answers in the positive, tells us that yeah, you can wish a blue K27 and a red K568, and it doesn't tell you how big your system should be for that to happen, but it tells you that if you go large enough, there will be a large enough complete graph such that no matter how you color its edges with two colors, you will get one of those at least. Okay, so so now so let's define Ramsey numbers, and then we'll prove the theorem. So n and m positive integers. Then the smallest, the Ramsey's theorem just says there is some s, some positive integer, but the smallest positive integer such that Ks arrows to Kn comma Km is denoted by R and M, and that's a Ramsey number called a Ramsey number. Okay. Sometimes when we are looking at what is called diagonal Ramsey numbers, R and N, like the ones we were looking at, R33, when the two wishes are the same, you drop the comma and n and you just write R, R, N. So we have shown that R3 is 6. It's also true that RMN is RNM. If I can guarantee you whatever S is, RMN is, that guarantees you a blue KM or a red KN, there's nothing so special about blue and red. You could just switch their places, and you will also be guaranteeing a blue KN and a red KM or a red KM. So RMN and RNM are going to be the same. What's R1M? That means that how many things do I need so that if I color all the edges, I'm guaranteed a blue K1 or a red KM. What's a K1? K1 is just a vertex. What's a blue K1? Well, when we say a blue something, we're talking about the edges. A K1 is just a vertex, doesn't have any edges. So it's blue already. So no matter how small my system is, this is guaranteed. So R1M is just 1. If you start with just one vertex, no matter how you color the edges, well, you don't have any work to do, then you will find a K1 such that all of its edges are blue. It doesn't have any edges. So all the edges it has, which are none, are blue. Now, what about R2M? So you might want to stop the video and think about what R2M is. So that means what's the smallest number such that if I take a K with a complete graph with that many vertices and color all the edges, I'm guaranteed a blue K2 or a red KM. A blue K2 means what? 2 vertices and an edge between them. It's just an edge. So how big should my system be so that I'm guaranteed either a red KM, that's a huge thing with lots of things in it, or a blue edge? And the answer is, think about it, it's M. Why? Well, because if you have M vertices and connect all of them, and then try to color the edges with blue and red, either you use the blue color somewhere or not. If you do, as soon as you do, you've got your blue K2. Or you don't use blue at all. If you don't use blue at all, then you're using red everywhere. And then the whole thing is a red KM. Okay. So now there's a little point here that I want to make that might be confusing. And in the first reading, you might want to ignore what I'm about to say, but it is sort of important. Does K5 arrow to K2 comma K6? So that means that if I color the edges of arbitrarily, the edges of a K5 with 2 colors, blue and red, will I always be guaranteed a blue K2 or a red K6? And the answer is no. And it's easy to see why, because if you take a K5 and color all the edges with red, then you won't have a blue K2 and you will not have a blue K6. You'll have a blue K5, but you won't have a blue K6. This is even the case. I mean, you can't tell me, oh, but I have a blue K2. That doesn't make any difference. Because what you have to tell me, if the answer was yes, is that you guaranteed to me a blue K2 or a red K6. When I tell you what my wish list is, I'm fixing my colors. I'm saying which one I want this color and which one I want that color. You can't change that in midway through the way and at the end say, oh, look, I found this other one. That's no good. I asked for a blue K2 or a red K6, and that's what I'm looking for. And it's K5 does not guarantee that, because you can color the edges of K5 all with red, and then you would not have a blue K2 and you would not have a red K6. Okay, so finally we're ready to, am I going to prove the theorem? I'm going to prove the theorem, but in a future video. I'm not going to do that in this video. In the next immediate video after this, I will give you a proof of Ramsey's theorem, which is a very nice proof. You definitely want to watch that video. I want to talk about something else now. R22 is 2. We said R2M is M, so R22 is 2. So if you just want an edge of, you just need 2 vertices, and you're either going to color it red or blue, and then you'll have a blue edge or a red edge. And R33 is 6. We proved that also. R44 is 18. We did not prove that, but I will prove that in a later video. And so my question to you is that, what do you think R55 is? Do you see a pattern from these numbers? You might want to stop the video and think about that. So you might think that, well, look, 2 times 3 was 6, 6 times 3 was 18. So maybe R55 is 18 times 3, which is 54. That's not the case. In fact, R55 is not known. It's unknown. It's an open problem in mathematics, and it's not for lack of trying. Is one that we haven't been able to find yet. The best we know is that it's a number between 43 and 48. The fact that it's greater or equal to 43, so what that means is that 42 doesn't work, so you need an example with 42 vertices, so and a particular coloring to and no R5 of either color. That was proved in 1989. The other direction, that it's less than or equal to 48, which means that if you have 48 vertices, then you are guaranteed a K5 of one color, a K5 of the other color, was only proved in 2017. And so it's quite a recent result. And you may want to think about, why can't we just try all the cases with a computer? And if you do a simple calculation, you will see the number of cases that you will have to check is tremendous. It's most likely more than the number of atoms in the universe. That if you just want to, by brute force, without thinking about it, just tell the computer, take for example a K47, color all the edges, do all the possible ways that you can color the edges with two colors, and for each of them check to see if you have a monochromatic this or that. That's not something a computer can do at all, no matter what. Even if you come up with a computer that it's a million times faster than the computers we have now, you can't do that. In fact, a famous combinatorist, maybe the most famous combinatorist, Paul Erdős, had a little story that he would say. He would say that if one day aliens invaded Earth and they said that we're going to spare you if you tell us what R55 is. That's all we want. We want to know what R55 is. And if you tell us that, we'll let you go. Otherwise, you're in trouble. If that's what they asked for, and if they give us a year and we put all of our resources together and so on, we probably could come up with an answer. But if they asked for R66, then it's hopeless. We better attack first. In fact, most of these Ramsey numbers are not known. So for example, R46, it's known that it's between 36 and 40, but it hasn't been pinpointed exactly what it is. By the way, R55 is conjectured to be 43. Sort of an educated guess is that it is actually 43, but we don't have any proof for it. R66 is the best that we know as of now, is that it's between 102 and 161. But again, and there's plenty of these Ramsey numbers, some of them that are known, and we will talk about them in later videos. But most Ramsey numbers are yet known, and they are not yet known. And some bounds exist, but there's some general bounds that work for everything. But precise answers are subject of current research. And if you look in combinatorics papers, there will be all kinds of papers about Ramsey theory. Okay, so looking ahead, the next video will be about a proof of Ramsey's theorem in the case of two colors. I mean, the theorem that I mentioned in this lecture, I'll give you a proof. Then there's the matter of small Ramsey numbers. We've already talked about R33 being 6. That's the only one we proved. But R44 is 18, R34 is 9, R35 is 14. And these are all sort of doable proofs up to a point. The examples are a little bit complicated to look at to see why we can't do better, but the proofs are certainly doable. We can do multicolor Ramsey theorem and Ramsey numbers. So instead of two colors, we can have 37 colors, and say that we're going to color the edges of a complete graph with 37 colors. And then I want maybe a K3 of this color, a K4 of color 2, and a K3 of color 3, and so forth. Have a long wish list. And Ramsey's theorem will tell you that that's possible. You might have a very large system to be able to guarantee that, but sooner or later you will do that. And that's sort of more in line with this idea that you can have this sort of varied wish list of many different things, And if the system is complex enough, you're guaranteed that it will happen. You could have something called graph Ramsey numbers. So instead of our wish list being about wanting complete graphs that are monochromatic, you might pare that down. You might say that I want a cycle that's blue and then a bipartite graph of blah size that's red. And I want one of this or that. Can I do that? And again, and that certainly you can do that because the complete graphs will give you a bound on that, because these are smaller graphs. They're easier to achieve than the complete graphs. And finally, there's something called hypergraphs, and there's Ramsey's theorem for hypergraphs. That will be a subject of a much later video later on. All of these are dealt with at some level or another in my book, and some of them will be subject of later videos. See you at the next video.